So how to search for maxima or minima? How to search for those points at which the function attains either its maximum value or its minimum value. So we suppose here that let's say we have a function f, and this function has a maximum, or let's say this function has a minimum in a bounded interval, and we can also think of the function having both maximum and minimum in that bounded interval. The point that we are trying to make here is that we have a function f, and the function is defined in a closed bounded interval I, and the function has got either a maximum or it has got a minimum in this interval, or let's say the function has got both in this interval. Now, the optimum point, the maximum point or the minimum point in the domain of this function, that optimum can occur either at the interior point of this interval, or that optimum can occur at one of the endpoints. When I say optimum, I mean that point at which the function attains either its maximum or its minimum. So the optimum can be either a maximum point or a minimum point. Let's say the optimum occurs at the interior point, or let's say it's inside the interval I, and also the function f is differentiable. Then in that case, as we have already covered, then the derivative f prime is going to be 0 at that point. That's definitely a necessary condition. So the point to note is here, if we talk about the optimum, and when I say optimum, optimum can be either a maximum point or a minimum point. So the optimum must occur either at an interior point of I or at one of the endpoints. Now, first we suppose that the optimum occurs at an interior point. The optimum occurs at an interior point. That means it occurs inside the interval I. Also, f is differentiable. Then we know that the derivative, this implies the derivative f prime will be equal to 0 at that point, That means at the optimum. And the optimum belongs to the domain of the function. Now in this case, I know that if the optimum occurs at the interior point and also f is differentiable, then the derivative f prime is going to be 0 at that point. It's going to be 0 at that optimum point. So, and before that we said that the optimum can occur either at the interior point, either at an interior point of I, or it can occur at one of the endpoints. So what we have to understand is that there are three types, and in fact I can say that there are three types of optimum points, or there are three types of extreme points. So given all this, I can say that there are three types of optimum points, or there are three types of extreme points. What I mean is there are three types of maximum points or minimum points or extreme points. The first is interior points in I, and here we have to understand that here f prime x is going to be equal to 0, because as we have just understood that if our optimum is if our optimum is inside the interval I, and when f is differentiable, we are going to have f prime x being equal to 0. So in that case, so the one type of an extreme point would be an interior point in I where f prime x is 0. Second would be endpoints of I where the function attains either a maximum value or a minimum value. In that case, the endpoint would be the optimum point, or the endpoint would be the extreme point. Endpoints of I. And the third is points in I. Points in I, that means points inside the interval I where f prime does not exist. That is also a possibility, that point in the interval I, inside the interval I, where f prime does not exist, but that point is either a maximum point or that point is either a minimum point. So that point will then be the optimum point or the extreme point. If we are concerned about this third type, we can see that in that diagram. So this is the diagram wherein we see that if I look at the figure 9.3, here we see that there is a minimum which occurs at point D. And so D is inside the interval I, but here f prime does not exist. We see that the function is not differentiable at point D, but we also see that the minimum is occurring at this point little d. So this is an example of the third type of extreme point, that is points in I which are either a maximum, when we have a point in I, point inside the interval I, which is either a maximum point or a minimum point, but at that point f prime does not exist. So that is something we need to keep in mind, that this is an example of that third type wherein we see little d and this is a minimum point, but here I see that the function is not differentiable. So f prime does not exist at little d. Now, most of the functions economists study are usually differentiable everywhere. So we are not that much concerned about extreme points of the third type. We are not that much concerned about this. So let's suppose that I want to find the maximum. So this is what I am concerned about. Find the maximum and the minimum values of a differentiable function. As I said, most of the functions economists study are usually differentiable everywhere. So we are going to start with a differentiable function only. And we are not considering the third case here, wherein there are points inside the interval I where f prime does not exist, and those points can be the optimum points. Yes, that can be a situation, but we are not concerned about those situations. As economists, we usually study functions that are usually differentiable everywhere. So let's say I want to find the maximum and the minimum values of a differentiable function function f which is defined on a closed bounded interval. A closed bounded interval AB. Now, if I want to find the maximum and the minimum values of a differentiable function f, which is defined on a closed bounded interval AB, what are the steps that I have to take up? The first step is we find all stationary points of f. We find all stationary points of f inside that interval. So that means I would like to find all stationary points of f in this. So that means I would like to find all x belonging to this that satisfy f prime x equal to 0. That would be the stationary point. So I would like to first find out all the stationary points. The second step is to evaluate f at the endpoints. At the endpoints A and B of the interval. And also I would evaluate f at the stationary points. So I found all stationary points of f in step 1, and the second step consists of evaluating the value of f at the endpoints A and B of the interval, and also at all the stationary points I found in step 1 of the interval, and at all stationary points found in the previous step. And the third step is, and the third point to note is that the largest function value we find in step 2. So the largest function value would be the maximum value. The largest function value in step 2 is the maximum value of f in AB. And the fourth point to note is that the smallest function value in step 2 is the minimum value of f in AB. So here we have evaluated f in step 2. What we do is we evaluate f at the endpoints AB of the interval, and we also evaluate f at all stationary points. And in this case, the largest function value would be the maximum value of f in AB, and the smallest function value would be the minimum value of f in AB. Now, the very important point to note here is that I started out with a differentiable function. I started out with a differentiable function f, which is defined on a closed bounded interval. And we know that if we have a differentiable function, it is definitely continuous. And so going by the extreme value theorem, we are assured that the maximum and minimum points do exist. because if I get back to the extreme value theorem, we know that if a function f, if it is continuous in a closed bounded interval a, b, then that function attains both a maximum value in that interval and a minimum value in that interval. So the point to note here is that we started out with a differentiable function, and we know that that differentiable function is surely going to be continuous, and that means we can take help from the extreme value theorem, and we can be assured of the fact that in this case, in this scenario, the maximum and the minimum points will exist. So keeping all that in mind, we now take up this question. Find the maximum and minimum values of this. F of x is equal to 1 by 9 x cubed minus 1 by 6 x squared minus 2 by 3x plus 1. And here x belongs to this. Clearly, I know that the function is differentiable everywhere. So the first step is to calculate f prime x, and I know that f prime x is going to be equal to 1 by 9 into 3 x squared minus 1 by 6 into 2x minus 2 by 3. So it is going to be equal to 1 by 3x squared minus 1 by 3x minus 2 by 3. And in this case, if you can see this, we can take 1 by 3 out. We can take 1 by 3 out, and we have x squared minus x minus 2. And if I just take up x squared minus x minus 2, so we need two numbers whose product is minus 2 and their sum is minus 1, and those numbers would be minus 2 and not minus 2 and 1, those numbers would be 1 and minus 2. So if we take up 1 and minus 2, 1 minus 2 is minus 1, 1 multiplied by minus 2 is minus 2. So that gives us 1 by 3 x plus 1 x minus 2. And from this, I can see that if I put f prime x is equal to 0, so f prime x, if I put that equal to 0, that means I see x equal to minus 1 and I see x equal to 2. And if we take up that interval, the closed bounded interval on which the function is defined, and we just think of those points inside the interval, and we see that this minus 1 and 2, these two are in this interval. So minus 1 and 2 do belong to this. So they do belong to inside of the interval. And that means in this case, so I know that x is equal to minus 1 and x is equal to minus 2. These are two stationary points. And what we have to do now is, so the first step was find all stationary points of f in AB, that open interval. That is, find all x belonging to that open interval such that f prime x is equal to 0. So we know those two stationary points in this case. One is minus 1, the other is 2. And now what we have to do is we have to evaluate f at the endpoints, which are minus 3 and 3, and we have to also evaluate f at all stationary points that we found, that is minus 1 and 2, and then we can get to the maximum value and the minimum value. So, and why do I say we can get to both the maximum value and the minimum value? Because here I know that the function is differentiable in this closed bounded interval, and that means the function is going to be continuous in this closed bounded interval. And if that is the case, with the help of the extreme value theorem, we know that a maximum and a minimum will surely exist. So what we see here is that now we are going to evaluate f at these points. So first we think of f of minus 3, and f of minus 3 is going to be equal to, so we put minus 3 in this case, and f of minus 3 is going to turn out to be minus 3 by 2. Then we evaluate it at x is equal to 3, so f of 3 is actually equal to 1 by 2. Now we go for f of minus 1, because we know that these are the stationary points, f of minus 1, and then I also calculate f of 2. f of minus 1 is 25 by 18, and f of 2 is going to turn out to be minus 1 by 9. So then we know that the largest function value is the maximum value, the smallest function value is the minimum value. So what is the largest function value in this case? The largest function value in this case is, the largest function value here is this. So this is the maximum value. And the smallest function value would be the minimum value. So the smallest function value we have is this. This is the minimum value. So we are now done with this question, and the question was find the maximum and minimum values of this. So the maximum value is 25 by 18 at x is equal to minus 1. The minimum value is minus 3 by 2 at x is equal to minus 3. Now let's take up another example. Let's say we are considering a firm, and the firm is producing any commodity, and the goal of the firm is to maximize the profits. Now the total revenue generated in a certain period, and the firm is, let's say, producing and selling Q units, the total revenue generated in that period, let's say, is R of Q dollars. This is the total revenue generated. So this is the total revenue generated. And this denotes, or let me just not take the case of dollars here. I mean, we can easily do away with that and still retain. Okay, so what I can do here is that I can write that this is the total revenue generated, that is RQ dollars. In fact, I can just say that and not write it here. Total revenue generated, and the cost associated with the dollar cost associated with producing and selling Q units is this much. So this is the total cost. And the profit obtained as a result of again producing and selling Q units would be total revenue minus the total cost, and profit would then be this. This is the profit. Now let's say there are some limitations faced by the firm, some sort of technical limitations, and keeping those limitations in mind, we suppose that let's say there is a maximum quantity that can be produced by the firm in any given period, as in the firm just cannot go on producing above that quantity. So the maximum quantity that can be produced by a firm in a given period that is Q bar. And that means if we are concerned about R and C, we are concerned about the revenue function and the cost function. So let's just assume that these two functions are differentiable. They are differentiable functions of Q. Obviously R and C are differentiable functions of Q, and the interval is 0 to Q bar, keeping in mind the fact that we just cannot produce anything more than Q bar. So what we can here assume that R and C are differentiable functions of Q, and these are differentiable functions in the interval 0 to Q bar. They are differentiable functions of Q in this interval. Now obviously if these two are differentiable, profit function pi will also be differentiable, and if profit function pi is differentiable, I know it is continuous, and if it is continuous in this closed bounded interval 0 to Q bar, obviously that means that pi has a maximum value. That is exactly what we can deduce from the extreme value theorem. So that pi function has got a maximum value, and the maximum, obviously I know it can occur at Q is equal to 0. Theoretically it can occur at Q is equal to 0. The maximum can occur at what I just said is that pi has got a maximum value. Pi has got a maximum value. That is something what we can deduce from the extreme value theorem, and theoretically it is possible that that maximum value occurs at Q is equal to 0, or that maximum value occurs at Q is equal to Q bar. But if that's not the case, if the maximum lies in the interior of this interval, then obviously I know that this pi function is differentiable, and the maximum value, as in if the maximum value lies in the interior of this interval, or in that sense, if I talk about the maximum point, that would be Q star, and that's going to satisfy pi prime Q star being equal to 0. So what we have just said is that we know that R and C are differentiable functions of Q in the interval 0 to Q bar. Since profit function is equal to since pi Q is equal to R of Q minus C of Q, that means the profit function pi will also be differentiable. If it is differentiable, that means it is going to be continuous, and if it is continuous, with the help of the extreme value theorem, we can be assured of the fact that the profit function will have a maximum value in this closed interval 0 to q bar, and the maximum value can occur theoretically at q is equal to 0, or the maximum value can occur theoretically at q is equal to q bar. But if that is not the case, that means the maximum value would occur at a point which is inside the interval 0 to q bar, and that maximum point, or that production level q star at which the profit function attains its maximum, that would be characterized by the fact that the first derivative at that point, keeping in mind the fact that pi is differentiable, so the first derivative at that point, at that interior maximum point, would be equal to 0. So pi prime q star would be equal to 0, and that just means that r prime q star would be equal to c prime q star. So what we conclude here is that production should be adjusted to a point where marginal revenue is equal to the marginal cost, because we see r prime q star is nothing but marginal revenue, c prime q star is nothing but marginal cost. So what we see here, and that's the necessary condition for that interior point q star to be the maximum, to give us that maximum profit, is that we have to adjust production to a point where marginal revenue is equal to marginal cost. Now, given all this, let's assume that the firm is, let's say the firm is getting a fixed price. Let's say the firm is getting a fixed price P per unit sold. So P per unit sold, this is the fixed price received by the firm. Now in this case, R of Q would be equal to P multiplied by Q. And that means if I want R prime Q star, that would just be equal to P. So my condition would be this: P is equal to C prime Q star. This would be my condition. This is a case wherein the firm has got no control over the price. This is a case wherein the firm is a price taker, or what we call a perfect competition. Now this is a case wherein the firm has got no control over the price. The firm is getting a fixed price P per unit sold, and that means that production in this case should be adjusted to a level at which our marginal cost is equal to that fixed price per unit of the commodity. Again, we are here thinking of the fact that the profit function does not attain a maximum at q is equal to 0. It does not attain a maximum at q is equal to q bar. We are again thinking of the profit function. Obviously, I know it is we are assuming that it is differentiable and it is achieving its maximum value in the interior of the interval 0 to q bar. So obviously from here I can say that if the firm has got no control over the price, if the firm has no control if the firm has no control over the price, production should be adjusted to a level at which marginal cost is equal to price per unit of the commodity. Please keep this in mind that we are again assuming that the profit function does not attain a maximum at q is equal to 0 or at q is equal to q bar. It attains a maximum in the interior of that interval. So how do we get to the maximum value? Again, we get to those steps. We take up all the stationary points. That means we solve this. When I solve pi prime q star is equal to 0, that means I get this. I solve this. So I find the stationary points, and I also find out, obviously in this case I have assumed that the profit function does not attain a maximum at q is equal to 0 or at q is equal to q bar. What does that mean? That means what I do is I just take up all the stationary points from this condition that r prime q star is equal to c prime q star. I get all the stationary points. I evaluate the profit at all those points, and the maximum profit will give us the highest value of pi of q. So that's something we have to keep in mind. Now let us suppose, to understand it intuitively, this condition that marginal revenue is equal to marginal cost and r prime q star is equal to c prime q star, to understand it intuitively, let's just suppose that we want to increase production from the level q star. So this is exactly what we have covered earlier also, that let's say we have reached this level q star, and at q star I know my profit is maximized. At q star, let's say I want to increase production from this level q star, obviously by 1 unit. So we are thinking of increasing production from the level q star. So we have reached q star, and we know that q star kind of maximizes my profit, but I just want to understand that condition of r prime q star being equal to c prime q star in an intuitive manner. So what we suppose is that once we have reached q star, now we want to increase production from the level q star by 1 unit. So that means this q star becomes q star plus 1. Now if we are going to think of how much revenue will increase, so obviously revenue will increase when we increase the production level. So revenue will increase. In this case the revenue is this. In this case this is the revenue. So the increase in revenue is this. Now this again is approximately equal to r prime q star, because I'll just repeat this. When I talk about r prime q star, that is when there is an infinitesimal increase in q star. What is the change it's the change in the revenue for an infinitesimal change in q star, and that's nothing. If we have large production, then if you increase production by 1 unit, that's almost close to or approximately equal to what we call an infinitesimal increase. So that is why we say that R of Q star plus 1 minus R of Q star is approximately equal to R prime Q star. So that's the increase in revenue when I increase production from the level Q star by 1 unit. But also, if we increase our production, we are going to incur some cost. And our costs will also increase as we increase the production level. So associated with Q star, we have C of Q star. Associated with Q star plus 1, we have C of Q star plus 1. And I know that C of Q star plus 1 is surely greater than C of Q star. So that means I can now think of what is the increase in cost. What is the increase in cost when I increase production level when I increase production from the level Q star to Q star plus 1. So increase in cost is going to be C of Q star plus 1 minus C of Q star. Again, it's going to be approximately equal to C prime Q star, given the fact that there's in any way so large production that if you increase production by 1 unit, it's almost close to the production being increased by a really very small amount. Now, what we have here is that this is how much we gain when we increase production by 1 unit, and this is how much we lose. This is the increase in our costs, and that is the increase in our revenue. Now, what that equation tells us is that R prime Q star is equal to C prime Q star. What does that mean? That means what we gain from selling an extra unit is exactly offset by what we lose from producing that unit. So the marginal revenue of selling an extra unit is exactly offset by the marginal cost of producing that unit. That is what is reflected by that condition. So that's the intuitive logic. Let's now suppose, so here let me write that marginal revenue of selling an extra unit is exactly offset by the marginal cost of producing that unit. Now, in this case, let's just suppose, given all this, let's just suppose that there is a tax. There is a tax of $T per unit which is imposed on, let's say, production of the commodity. So there is a tax of $T per unit, or let's say this is imposed on the production of the commodity. So the profit function would be, so if this is the tax which is imposed on the production of the commodity, it is $T per unit. So our cost function would be this, plus TQ. This would be my new cost function. And that means my profit function would be this, R of Q minus C of Q minus TQ. Because now when you are selling Q units, you are actually accruing another cost, another additional cost of TQ, because T is the tax per unit that is imposed on the production of the commodity. If you are producing Q units, that means you are giving out a tax of TQ. So that's additional cost. Again, we are assuming that, let's say the maximum profit is not at q is equal to 0, it is not at q is equal to q bar. That means the maximum profit is going to occur at a level q star, which is inside that interval 0 to q bar, and at q star, pi prime q star will be equal to 0. At q star, the first derivative, obviously thinking of the fact that the profit function is differentiable, given that r of q is differentiable, and given that r is a differentiable function of q and c is also a differentiable function of q. Given all this, I know that pi is also a differentiable function of q, and I can see that here. Also, I suppose that the maximum profit is not at q is equal to 0, it is not at q is equal to q bar. So the maximum profit is going to occur at a level q star, which is again inside the interval 0 to q bar, and there pi prime q star would be equal to 0. So pi prime q here is equal to r prime q minus c prime q minus t. And that means if I think of the condition for maximum profit, this first derivative has to be 0, and that is r prime q star is equal to c prime q star plus t. So this is the condition for maximum profit if you also have a tax of $t per unit being imposed on the production of the commodity. So this is the condition for maximum profit, and what it says again is that when we increase production by 1 unit, what we gain is approximately equal to r prime q star, this one. And when we increase production by 1 unit, what we lose is approximately equal to this. So I know that c prime q star is my marginal cost, t, and t is also part of my marginal cost now, precisely because when I increase production by 1 unit, I have to pay out $t tax per unit. So again, in this case, the condition tells us that what we gain by increasing production by 1 unit from the level q star. Again, now we suppose that we are again contemplating, let's say, increasing production from the level q star by 1 unit, just to get to the intuitive logic. So we suppose we are thinking of increasing production from the level q star by 1 unit. What is it that we gain? What we gain is approximately equal to r prime q star. What we lose is approximately equal to c prime q star plus t, because also now we have to pay $t in tax for that extra unit of output that we have produced. So again, the condition tells us that the marginal revenue of selling an extra unit, again, it's exactly offset by the marginal cost of producing that unit. So it's almost the same. Logic being applied. Now let's suppose that we have a function f and it is differentiable in this interval AB, in this closed bounded interval AB, and let's say I know that x0 is a maximum point for f in AB. What I mean to say here is that the function f attains its maximum value at x0. The function attains its maximum value at x0. I know that the function is differentiable in this closed bounded interval. I know that x0 is a maximum point for f in that closed bounded interval. That just means that the function attains its maximum value. That just means that the function attains its maximum value at x0 in this interval AB. Let's say x naught is equal to a. Suppose x naught is equal to a. Let's say this is the case. Then if I think of f prime a, f prime a in this case, it just cannot be positive, because there will be points to the right of a where that function f has a higher value than at a. So the point to note is that if x naught is equal to a, then f prime a, it cannot be positive, because if f prime a is positive, that just means to the right of x there will be points, not to the right of x, I think I should just repeat this point. Let's say x naught is equal to a. We know that we are concerned about a function which is defined in the interval ab, in the closed bounded interval ab. So suppose x naught is a. I know that x naught is a maximum point for f in that closed bounded interval ab. If x naught is a, then f prime a just cannot be positive. It cannot be positive, because if it is positive, that means there will be points to the right of a where f has a higher value than at a, and that's not possible because x naught is a maximum point for f in that interval. Also, in this case, if x naught is equal to b, and I know that x naught is a maximum point for f in that interval, so if x naught is equal to b, then obviously again f prime b, it cannot be negative, because if it is negative, that just means that there are some points to the left of b, okay, where f has a higher value than at b, and that's again not possible because x naught is a maximum point for f in ab and x naught is equal to b. Also, if x naught belongs to this, if x naught lies in the interior of the interval ab, then, and I know that x naught is a maximum point for f in that closed bounded interval ab, and I also know that the function is differentiable in that interval, then f prime x naught is equal to 0. So we can actually take up these cases diagrammatically also. Here we can see that first we think of maximum at a. As I said, if x naught is equal to a, then f prime a, it just cannot be positive, and you can see here that it is not positive, because if it is positive, then that means there would be points to the right of a like this where f has got a higher value than at a, and that's not possible because the maximum is at a. The maximum is at x naught and x naught is equal to a. Also, if we take a look at the second diagram, and let's say I know that in this case, not the second diagram, the third diagram, let's say the maximum is at b. I know that the function is differentiable in this interval, in this closed bounded interval ab, and let's say x naught is equal to b. This is the maximum point of f in ab. Then in this case, f prime b, it just cannot be negative, and clearly we see that it is not negative here. Why can it not be? Why is it that f prime b just cannot be negative? Because if it is negative, that means there will be some points to the left of b where f has got a higher value than at b. And again, that's not possible because x0 is the maximum point for f in that interval, and x0 is equal to b, because b is the maximum point for f in this interval. Also, if we take up the last case, which is shown here in the middle, if x0 belongs to the interior of the interval, I know that x0 is the maximum point for f in that interval, and if that x0 lies inside the interval, then f prime x0 would be equal to 0. Then I know that the function, obviously I know earlier that the function is differentiable in the interval. I know that x0 is a maximum point for f in that interval, and if x0 lies in the interior of that interval, obviously in that case f prime x0 would be equal to 0. That is, the tangent to the graph of the function at that point has to be parallel to the x-axis.